In this video we're going to learn how to find the coordination number of a crystal lattice. And we're going to do so with 5 different examples. A one-dimensional example, a two-dimensional example, and 3 examples in 3 dimensions. The simple cubic, the body-centered cubic, and the face-centered cubic. But what actually is the coordination number? It is defined as the number of atoms that are the shortest distance from a given atom. That means we're going to pick one atom from the grid as our observation point, so to speak, and then we're going to look for the nearest neighbors of that atom. Suppose we have this one-dimensional grid here, which is essentially just a line with lattice points of equal distance, and we picked this one right here as our observation point. The nearest neighbors of this lattice point are obviously going to be these two. This one has twice the distance, so it's not the nearest neighbor anymore, and this one is even further away. So these two right here are the nearest neighbors, which means that this hypothetical oversimplified lattice has coordination number 2. Let's look at a two-dimensional example. We have chosen this one as our observation point, and now we have to look for its nearest neighbors. Of course, all of those are neighbors, but only the ones connected with straight lines are the nearest neighbors, because this diagonal is longer than the straight line. So the shortest distance is this one. There are 4 of those, which means that this grid has a coordination number of 4. Now in 3 dimensions things get a bit more complicated, but the principle is exactly the same. What we need to keep in mind for this model is that atoms are treated as solid spheres. And if you have 2 solid spheres, the shortest possible distance between them is obviously touching distance. So when trying to find the coordination number of a 3-dimensional lattice, before we do anything else, we have to look at the lattice as a 3-dimensional model and think about where and how the atoms touch. Suppose we have a simple cubic, which means that our grid is a cube with a lattice point or an atom in each of the corners. The simple cubic is defined in such a way that the length of the edges is twice the radius of those atoms, which means that the atoms touch along the edges. So if we now transfer this to our simplified drawing here, it means that the shortest possible distance we have to look for are the edges of the cube. If we pick this one as our observation point, we can see that it has 3 immediate nearest neighbors in its own cube. But of course those crystal structures consist of much more than just one unit cell. So each of those cells is surrounded by others. And if we take its neighbors into consideration, there's another nearest neighbor here, one nearest neighbor here, and another nearest neighbor here. Of course, technically there would be a lattice point here as well, but this distance is a diagonal and thus longer than these 2 distances. So the simple cubic has a coordination number of 6. Next, we're going to take a look at the body-centered cubic. The body-centered cubic is defined in such a way that we have one atom in each of the corners and another one right in the center of the cube. Transferring this to our simplified drawing, we have again, one in each corner, and another one right in the center. Now, if we take a look at this 3-dimensional drawing of the body-centered cubic, we can see that in order to squeeze the central atom in, the atoms along the edges need to be further apart. So we have no touching along the edges anymore. We also have no touching along the face diagonal, but they do touch along the body diagonal of the cube. And if each of the corner atoms touches the central atom, we get 1, 2, 3, 4, 5, 6, 7, and 8 nearest neighbors. So the coordination number for the body-centered cubic is 8. Now, admittedly, we have made this a bit easy by choosing the central atom as our observation point. But one of the things that makes the coordination number so special is that it remains the same no matter which atom you look from. So just to show that, we have this stack of 8 of those cells. We found out that in the body-centered cubic, the corner atoms always touch the central atom. Since this is a corner atom, it has to touch the central atom of this unit cell here. But it is just as far away from the central atom of this cell, this cell, this cell, this cell, this, and this. So, since this corner atom has to touch the central atom of each of the surrounding cells, its nearest neighbors are going to be the central atoms of the upper back left cell, the upper back right cell, the upper front right cell, the upper front left cell, blah blah blah, etc. And since we have 8 neighboring cells, we also get 8 nearest neighbors for this corner atom right here. So yes, this makes it easier because you can stay within one unit cell and you don't have to draw more of them, but the coordination number remains the same no matter which atom within the lattice you're looking from. As our last example for this video, let's take a look at the face-centered cubic. It's called face-centered because in addition to the 8 corner atoms, it has one atom in the center of each of the cube's faces. In our simplified drawing, that means we have, again, 8 atoms in the corners, but also one in the front wall, one in the back wall, one in the left wall, one in the right wall, one in the ceiling, and one in the floor. Now, since we have to squeeze in all of these face atoms, the corner atoms are too far away to touch along the edges, and we also have no touching along the body diagonal. This time, the touching distance is the face diagonal, and that's what we have to look for. So the shortest possible distance for this lattice is from the center of an edge atom to the center of a face atom. We're going to choose this corner right here as our starting point. And for the face-centered cubic, I usually find it easier to look at the different planes within the structure one by one. So we have this plane right here that includes 4 faces, this plane right here that includes 4 cube faces, and we also have this plane right here that includes 4 cube faces. Let's start with this one. Recall that the shortest distance for the face-centered cubic is from the corner to the center of the face, and that distance is obviously the same for all of those faces. So in this plane, we have 1, 2, 3, 4 nearest neighbors. Next, we're going to take a look at this plane right here. Again, we have 4 faces. The shortest distance is from the corner to the center of the face. So we get 1, 2, 3, 4 nearest neighbors. And lastly, we're going to take a look at this plane right here. Again, 4 faces, a nearest neighbor in the center of each of those faces. So we have one in the center of the upper right face, one in the center of the upper left face, lower left, lower right. In total, that makes 12 nearest neighbors, so the coordination number of the face-centered cubic is 12. I really hope you found this video helpful and it made the topic a bit clearer. If yes, consider leaving a like or sharing it with a fellow student who might also benefit from it. Thank you so much for watching and see you in the next one.